Okay, so good morning. Thank you very much for your attention. It's always good to give your lectures early in the school before people begin to wither away. So the arrangements for this course are going to be a little unusual, but I hope it'll be clear. I have a bunch of lecture notes which I'm not going to show you in these lectures. I'm going to lecture on the blackboard. But there will be lecture notes which you will find on the Indico page. Presumably after the lecture you can go and study them. I'm going to show some figures from those lectures on the screen here as we proceed. So that'll be the setup for the 4 lectures. The course of lectures that I'm supposed to give is the Standard Model and its applications to the Higgs Boson. And so that's more or less what I'm going to talk about. The 4 lectures are divided in the following way. The first lecture will be a more or less a remedial course in weak interactions for those of you who may not have seen all of this material in your courses. Theorists consider themselves very sophisticated about the Standard Model, but sometimes when you ask theory students questions, it turns out that they're not as sophisticated as they think. So I hope that this lecture will be at the right level. If you think this lecture was elementary school, come and complain to me, and I can raise the level in the subsequent lectures. On the other hand, if there's a lot of material in this lecture that you haven't seen before, or that you haven't seen presented in the way that I'm going to do it, I'd also like to know that, so again, I can think about the level of the next 3 lectures. The second lecture will be about a very important principle in the Standard Model called the Goldstone boson equivalence theorem. This is the statement that W and Z bosons, when they're accelerated to very high boosts, the longitudinal part resembles the Higgs boson, which was necessary to give that boson a mass. And this is it's actually a very subtle thing, because the use of this theorem is different in different processes. It has different implications for different processes. And I'd like to kind of go through the different ways that this theorem appears in some illustrative particle physics processes. Lecture 3 will be about the Higgs boson in the Standard Model. And again, this will be kind of the course in what are the interactions of the Higgs boson and how is that reflected in its decay modes. And then the 4th lecture will be about what's called Standard Model effective field theory. And this is a formalism which is very much in use today. It's both used and abused. And I'm going to try and tell you what I think about this and basically how to apply it in various contexts. So that's more or less the menu for this course. The first 3 lectures of the course, a lot of the material will be similar to lectures that I gave at the CERN school a couple years ago. And you're lucky that I've actually written up those lecture notes, and you'll find it at this archive number. So I hope that if you look at that paper, it'll be a kind of very straightforward presentation of some of the things in the first 3 lectures. The 4th lecture, I don't know where what I'm going to present is written up well, but I'll give you some references when we start that lecture. Again, the CERN school is for experimenters. You guys are all theorists. But be careful. You might find the level of these lectures correct. And I would appreciate some feedback on that, as I say, to prepare my next few lectures. Another thing that you might want to look at, if you need a broader course in particle physics, is that I have actually a new book coming out called Concepts of Elementary Particle Physics. And the PDF draft is at this website. Don't click that on your phone. It's a 300-page book. But you might be interested in it. And it is within a month of going to the publisher, so I would really appreciate any feedback that you folks have on that. So this is supposed to be like the complete course of particle physics, but for those people who don't know any quantum field theory. So You folks all know quantum field theory, and I will assume that in these lectures, but hopefully there are things in there that will be useful to you. Okay, so let's get started. The purpose of today's lecture is to introduce, well, not introduce because you folks have seen a lot of this material before, but to tell you some things that you may not know, but on the other hand, it's very important to know about the theory of weak interactions. In particular, from experiment, why do weak interactions have the structure that they have? And how do we test that structure to a high degree of accuracy? A lot of the discussion in this lecture will be about E plus E minus collider physics. Now, probably there are some of you in the room who think that collider physics and hadron collider physics are synonyms. But actually, it's not true. Before you were born, there was a lot of discussion of E plus E minus collider physics. I was certainly involved in that way back in prehistory. And I think that there's a benefit to that because in electron-positron collider physics, you get to actually collide elementary particles. And so the couplings and angular distributions are actually directly displayed for you. Whereas at the LHC, what you find is you're always like doing these calculations, which have very simple structure, and then totally confusing that structure by integrating with parton distributions, doing jet selections, worrying about the backgrounds, which are similar to the reactions that you're looking at, et cetera, et cetera. And so I think for many students that leads to an over-reliance on Monte Carlo, and maybe not enough on trying to understand the physics nature of the basic elementary processes. And so there'll be a lot of emphasis on that subject in this lecture and actually in all of the lectures in this course. So let me begin by just writing down some things that I hope are really second nature to you, but I'm going to use them very strongly in this lecture. So first of all, those of you who have studied my book know that I like to work in the, first of all, for all particles in helicity amplitudes, and in particular for massless particles in the helicity basis and the corresponding basis of gamma matrices. So for this lecture, the gamma matrices are always going to be in this form, which emphasizes helicity. Sigma mu is 1 sigma. Sigma bar mu is 1 minus sigma. In that basis, the left and right-handed components of a Dirac field will decouple. In fact, in that basis, the Dirac equation, maybe I should have written this first. The four-component Dirac wave function breaks up into psi L and psi R. The Dirac Lagrangian takes this form in which psi L and psi R are totally decoupled. And the mass term is a mixing between psi L and psi R. So it's psi L dagger psi R plus psi R dagger psi L. And this equation it's a very useful equation in two different ways. First of all, in many of the experiments that I'll be talking about today, it's correct to ignore the fermion masses. For example, when we study the Z boson with high precision, the Z is at 91 GeV. The B quark has a mass of about 4 GeV. And the corrections that come from the B quark mass are mb squared over mz squared. So it's 4 over 91 squared. It's 1% or so. And so then even the bottom quark mass can be ignored to a first approximation, at least when we do calculations. So I'm going to make maximal use of that throughout these lectures. The second thing is that you see that if the theory is massless, the psi left and psi right are completely independent from one another in the Lagrangian. I guess if you're a very sophisticated theorist, you'd say, well, they're linked through anomalies. In general, I'm not going to emphasize anomalies in this course, but if you're curious, you can ask me offline. In any event, in order to give a mass to any particle, you need to link together the left and right-handed components of the fermion field. Now, in quantum electrodynamics, this is a very straightforward thing to do, because the left and right electron fields in quantum electrodynamics have the same quantum numbers. The only relevant quantum number is electric charge, and left and right-handed electrons have the same electric charge. But in the weak interactions, it's totally different. The left and right-handed components of the electron field, and actually of all fermions, have different SU2 cross U1 quantum numbers. And so therefore, this term here is forbidden by the gauge symmetry of the weak interactions. And that's maybe the most important statement that you have to understand about the weak interactions. And in particular, that's the reason why the Higgs boson, for better or worse, is necessary in our theory of elementary particle physics. And so I'd like to, first of all, give you a little of the experimental background of that statement, tell you a little about the structure of the standard model of weak interactions, and then discuss the precision tests of that model, especially in measurements at the Z boson. So let's just consider this a little further. I'd like to write some consequences of this structure. For a massive fermion, if you solve the Dirac equation, you get some four-component U and V matrices. I'll write four-component things with capital letters. What goes up here is the left-handed and the right-handed components, and in a massive theory, they're mixed by the mass term. So what goes up here is basically E plus P times a spinner, which represents the spin direction of that fermion, and the square root of E minus P down here. And for the UL, just the opposite. E minus P upstairs and E plus P downstairs. And as you folks learned in your field theory course, there's a similar structure for the V matrices that represent antiparticles. When you have a massless particle, the top is supposed to decouple from the bottom, and you see that happening. So for example, for a massless particle, we can just ignore half of this, and then you would get something like UR, which would be the top part, is the square root of 2E times whatever the spinner is, and UL is again the square root of 2E times the spinner. But now it has to be a special spinner. For example, for the momentum parallel to the 3 direction, this has to be spin up, and this one has to be spin down. So the top entry here will represent a massless fermion with its spin propagating in the right-handed sense. The bottom one is a massless fermion with its spin in the left-handed sense. And those are the only particle states, positive energy solutions to the Dirac equation, which are allowed for massless particles. The antiparticles of these particles, as you know, are the V left, whose wave function is the square root of 2E. It's again only present in the upper components. But remember, for an antiparticle, the spin is the opposite of what appears in the spinner. So this would be down. And for a V right, which is the antiparticle of this particle, you would get something like that. Okay. If you put these spinners together, you find the helicity conserving vertices for spinners to go to a vector boson. And so, for example, for E left, E right, let's call this the 3-axis. What you have here is 2E, which is S. And then if you actually work out the vertex here, it's U dagger sigma bar mu V. You find the following expression, the square root of 2, and then the polarization vector in the minus direction. So this vector here would be 0, 1, minus I, 0. It's the polarization vector for a left-handed spinning spin 1 object. And so that tells you that the photon or Z boson, the virtual photon or Z boson that you create here, has the quantum numbers j equals minus 1 in the 3 direction. So it's exactly the propagation of angular momentum from the initial state to the intermediate state, and then when you look at a fermion final state, to the final state.
This minus sign doesn't appear in this, and you know in the SEL.
Oh.
Is it important somehow?
This minus sign?
Yeah,
It's, if you, I'm very sloppy about that minus sign. Please excuse me. It's absolutely irrelevant as long as the particles are absolutely massless. If you have massive particles, it comes into some of the interference terms. So you just have to be a little careful about that. Oh, it may or may not be present in this formula. Please excuse me. So then finally, if you put this together into a, if you like, a full structure of an amplitude, the simplest thing to think about is E plus E minus to, let's say, mu plus mu minus, where we have left-handed electrons and left-handed muons. By helicity conservation, this has to be a right-handed guy. The amplitude will then be something like 1 over q squared or 1 over q squared minus mz squared. Let me just put it for a photon. A coupling squared in the numerator. And the dot product of 2 of these polarization vectors. And so that dot product is 1 plus cosine theta for this process. And for the opposite process, it'll be 1 minus cosine theta. So this creates 2 sets of formulae that, I guess, if I were you, I would just commit these to memory because they just come up all the time. The cross-section for a left-handed electron to go to a left-handed muon for mu left, it's proportional to 1 plus cosine theta squared, the square of this thing. It's proportional to 1 minus cosine theta squared for a mu right. And another way to write this is that the square of the amplitude, well, again, the cross-section, is proportional to, if you look at this object, it's t over s squared. And here, u over s squared, and here t over s squared. Or to put it another way, let's call this P1, P2, P3, and P4. Okay, so how many of you have seen all these formulae before? Please raise your hand. Okay, this is good. For those of you who have not seen these formulae before, these are really easy to derive. How many of you are amplitudes people? Raise your hand. Ah, okay. So this you recognize as just the square of the spinor products. So then it's trivial to derive that. And for those of you who are not amplitudes people, ask amplitudes people what I just said. Okay. So in any event, for a process like this, it's just really easy to visualize what's going on, all the spin dynamics. These formulae directly reflect the fact that the initial helicities of the electron and positron are transferred in the way I said to the final state fermions. And now let's try and make some good use of this in trying to understand the structure of the weak interactions. So the next thing I'm going to do is race through, in a similar way, some essential phenomenology of the weak interactions before you get to the unified SU2 cross U1 theory. And once again, this is stuff that I hope you have seen, but we'll take a little poll of how much of this you have seen and how much is new to you. Well, let me ask you this question. Why don't I just start with you folks? The crucial feature of the weak interactions, before we talk about neutral currents or anything like that, is the V minus A interaction. That is the fact that at low energy, the matrix element of the weak interactions is 4G Fermi over the square root of 2 times J plus dot J minus, where J plus is an isospin raising left-handed current, like nu dagger sigma mu E plus U dagger sigma mu D plus dot dot dot. And J minus is the conjugate of that, the corresponding isospin lowering current. Everywhere here, left and right correspond to the basis I was working in. That is, the top components of these spinners. Sorry. Oh, this is all screwed up. No one told me. Left is on top, right is on the bottom. So L always refers to the projection of the top component of these spinners. V minus A is not obvious. In fact, this was really the whole mystery of the weak interactions historically, and eventually the key to the unraveling of the structure of the weak interactions. An interaction like this manifestly violates parity, because parity interchanges the left and right-handed components of fields. It turns a right-handed spinning particle into a left-handed spinning particle. And parity in the early 1950s was considered an inviolable principle of nature. After all, parity had been tested in atomic physics and in nuclear physics, and it seemed very non-trivial at the time that it basically worked perfectly in both of those domains. This led to mysteries in elementary particle physics in the 1950s, where people interpreted results assuming parity conservation and found that particles that seemed to be identical were produced in parity reversed reactions. Most noticeably, the K-meson, the neutral K-meson, was produced both as a parity even particle and a parity odd particle. And people said, how could this be? You all know, I guess, that Li and Yang broke this logjam by saying, number one, there was something called the weak interactions, which was different from the nuclear forces. And number two, parity conservation had never been tested specifically in the weak interactions. And this is a very, if you like, it's a very simple observation. It's commonplace to us now, but it was sufficiently important in the 1950s to give those guys the Nobel Prize. And almost immediately it was discovered that in specifically the weak interactions, in beta decay, other low-energy particle decays, parity conservation was not only violated, but it was violated maximally. That is to say, the left-handed components of fields participated in the weak interactions. We're now talking about the charge-changing weak interactions. But the right-handed components did not participate. So now, after decades of experience, we have some really striking examples of V minus A, where there are really qualitative things about particle physics that V minus A is necessary for these things to happen. And I'll make a little list of them here, and I'd like to go through at least 3 of them. The 4th one I think I'm going to leave to you to investigate. The first one is just that V minus A implies that when you have beta decay, the beta decay electron is polarized in the left-handed sense. So that's kind of obvious. If the left-handed electron participates in beta decay and the right-handed one doesn't, you get polarization. The second one, which was really some of the principal early evidence for V minus A, is in the structure of mu decay and the so-called Michel parameters. The third one is the decay of pi to mu nu. And the fourth one, which I might actually not talk about here, but it'll be in the lecture notes, is the Y distributions in neutrino scattering. Maybe I should just take a poll. Does anyone know what this is? Anyone? Okay. Look in the lecture notes. It's quite an interesting story. I'll talk about the first 3, and these are things that really you should know. The first one requires just the formula that I have on the blackboard here once I've actually written it down correctly. The weak interactions, as I've said, couple to the upper component, the upper 2 components of this 4-component spinner. But what you see is that if I have a massive electron, the mass actually matters. The upper components are non-zero for both left-handed and right-handed electrons. And if you think just a moment, beta decay, that is the transition of one nucleus to another nucleus, or, well, I mean, beta decay, as you know, is the neutron going to a proton, an electron, and an antineutrino. The amount of energy liberated is of order MeV. So the mass of the electron is, in principle, in play here. And so we can't ignore the electron mass in this circumstance. Nevertheless, it's very simple to estimate the polarization of the electron. The polarization, in the left-handed sense, should be basically the probability that you make a left-handed massive electron over the probability that you make a right-handed massive electron. So it'll be something like the square root of E plus P squared minus the square root of E minus P squared divided by the sum of those things. So the polarization, we'll encounter this a couple more times in this lecture, is formally defined as the probability of a left-handed particle, or whatever, the probability of a left-handed particle minus the probability of a right-handed particle divided by the sum. It's always a number between 1 and minus 1. In this case, this is pretty easy to work out. The numerator is proportional to P, the denominator is proportional to E. This is the velocity of the electron. So what V minus A predicts is a striking regularity where, as you go to different nuclei and you look at different beta decay transitions and you measure the polarization of the electron, which actually typically is done with Mohr scattering, so it's a little imperfect, but if you're a clever experimenter, you can do it well. What you should see is a regularity where, as the electron becomes more and more relativistic, its polarization in the left-handed sense increases proportional to velocity until finally, for a very relativistic electron, only the left-handed state is produced and the right-handed state is not produced. So it's hard to find really current data on this, but here's a 1970s version of this data. And actually, it's pretty remarkable. Regularity is well preserved. I must say I don't understand the experimental problem here, but these are intermediate velocities. But you can see that as the electron becomes very relativistic, first of all, the polarization does go to 1, and actually it follows exactly the law that we've derived here in a very simple way. So V minus A. The second of the things that I have on this list has to do with the structure of mu decays and the Michel parameters. So how many of you have actually computed the observational form of mu decay? Anyone? Oh, this is a really nice exercise. It's done in my textbook in a you kind of have to cheat because I didn't assume that people knew the trace theorems. But since you guys know the trace theorems, or maybe this kind of regularity, it'll be very easy for you. Here are the basic ingredients. Let's do this over here. The process we're talking about is the muon turning into a muon neutrino, an electron, and an electron antineutrino. The coupling here is the, in the V minus A theory, is this coupling using this term with muons for the muon and the corresponding term here for the electron. So it's a point-like current-current coupling. And for that, as you know, the square of the matrix element, if these were all massless particles, it would be, let's get this straight. This guy is this guy is left-handed, this guy is left-handed, this guy is right-handed, and this guy is at rest. Now, if the muon were very relativistic in some context, you would, according to the formulae I wrote, you would put the left-handed momenta together like that, and you would put the right-handed momenta together like that, nu bar, and then there would be a factor of 4 here. And the right answer is that the muon can be at rest, but then, according to this formula, you only get half of the total result, so you get a factor of 2. So the matrix element is proportional to this factor. Now, if you have a muon sitting at rest, the 2 neutrinos are unobservable. They pass through all detectors. So the only handle you have is the electron. But the electron, because it's a 3-body process, has an energy distribution. And you can ask, what is the energy distribution of the electron? And that should be a definite function that we should be able to graph and compare to experiment. From this formula, it's very easy to work out that function. Let me just write down a couple formulae that you would need to know, which, frankly, you probably need to know anyway. So here we go. What we're interested in is d gamma, d electron energy. And we would write that in the following way. We need the integral over 3-body phase space, 1 over 2 mu, and the square of the matrix element. For a 3-body process, all of the massless particles, there's a very nice representation that we can use. We can write x mu is equal to 2p mu, xe, 2p mu dot pe over m muon squared, or in general, the total center of mass energy of the process. X nu is 2p mu dot p nu over m mu squared. And x nu bar is 2 p mu dot p nu bar over m mu squared. By momentum conservation, p nu plus p nu bar plus p nu plus pe equals the momentum of the muon. So the 3x's add up to 2. So 2 of them are independent. And if we integrate out all the other degrees of freedom in the problem, we have now a 2-dimensional integral over, let's say, xe and x nu bar, eliminating the third one. Now, you need the formula for 3-body phase space. And let me write this formula. Is equal to the integral dxe, the integral dx nu, let me write the third one, dx nu bar, delta of xe x nu bar, times some constant, which don't hold me to this, but I think it's 128 pi cubed. Is this a formula familiar to you? How many people know this formula? Raise your hand. Some. Okay. It's fun to derive this formula. It's also the basis for a lot of elementary particle phenomenology. I think if someone has a question about that, you should probably ask me offline, though. Now, I don't want to deal with the overall constant, although you see there is a large denominator, which means that 3-body decays in general and muon decay in particular are highly suppressed. It's probably this number which is most responsible for the long lifetime of the muon in practical circumstances. But what I'm interested in is the shape with respect to energy. So let's now translate this formula. P mu dot P nu bar, it's just, this is the mass of the muon. This is only, when you take the dot product, only the energy component matters. It's proportional to the energy of the nu bar, so this is an x nu bar. Now what about PE dot P nu? Let me put a 2 in front of it, because we're not keeping track of overall factors. This is PE plus P nu. This is P mu minus P nu bar squared. And then when you square this up, you can see that this is 1 minus, proportional to 1 minus x nu bar. So now we're doing excellently. This formula is proportional to the following thing. X nu bar, all of these variables go from 0 to 1. The maximal situation is when you have one massless particle recoiling against the other two. And then the energy of this guy is precisely half the muon mass. So with the 2 here, these all go from 0 to 1. We have an integral dxe from 0 to 1 minus x nu bar. That's as high as it can go. X nu bar times 1 minus x nu bar. And then you can see that this is going to be the integral dx nu of x nu times 1 minus x nu bar squared. And if you do that integral, you get x nu squared over 2 minus x nu bar, sorry. Oh, I did this the wrong way around. I'm an idiot. Just please excuse me. Oh, yeah, I am an idiot. I should have put this here. I should have put this here. Let's integrate it over the guy that we don't observe. That's the right thing to do. We just have this, and then you just do that integral. And you get the answer I was searching for, namely xe squared over 2 minus xe cubed over 3. So this is a very simple result. It's a very simple function. It's a function that has this shape. It goes between 0 and 1. You can check that the slope at 1 is 0. It starts like xe squared, so the shape here is parabolic, and it looks something like that. And so there's a characteristic function that looks like that, which is, this is the energy of the electron divided by the energy of the muon, and this is the rate, d gamma dE electron. And this is a directly measurable function. If you stop muons and then you measure the electron energies. In reality, it doesn't quite look like that. You have to worry about radiative corrections. In particular, the electron can radiate a photon. That will basically smear the endpoint, because there's always a radiated photon. So now this will look like this at the endpoint, and it will contribute something down here. So the actual radiative corrected function looks like that. And then you just have to imagine behind that there's an idealized non-radiative corrected function that looks like the yellow curve. Okay? Here's the data. Wow. It's just what I said it was. The solid curve is the radiatively corrected curve due to CERN and collaborators. You see the data. This is from a Columbia group in the 1960s. And this theory really works extremely well. So all the features of this formula are coming from the structure here, which is the current-current interaction structure, and the assumption of V minus A. Maybe V minus A is not so obvious here. But there's a twist on this, which actually is very cool, which was done in the 1980s at the Triumph Laboratory in Vancouver. One of the things that this structure implies is that if you're at the end point in the electron, you're in a situation where the two neutrinos are recoiling against the electron. I assume the muon is stopped. Now, please notice the electron is left-handed, the new mu is left-handed, and the new bar is right-handed according to V minus A. That means that if the muon is right-handed, or maybe I should say if the muon spin is pointing in the 3 direction, then this particular orientation is forbidden. Okay, it doesn't conserve angular momentum. The angular momenta here cancel. V minus A says the angular momentum of the electron, which is highly relativistic, is always negative. If the angular momentum of the muon is positive, then you can't go from here to here. If you were to reverse this configuration, so the electron comes out backwards with respect to the muon spin, that's the maximum. So you can really do this experiment. For reasons that I'll describe in a moment, you take a proton beam, you make pions, you let the pions decay to muons, you bring the muons around, and you stop them in some chamber. You have a magnetic field in this chamber, so the stopped muons undergo spin precession. And then somewhere over here you have a counter. The electrons come out, and you count the number of electrons with respect to the spin precession angle of the muons. So there's a Berkeley Triumph group that in the mid-1980s did this experiment. And what they found was, within the limitations of the experiment, essentially perfect extinction up here when the muon spin points to the detector. So when the muon spin is pointing at the detector, you get no electrons. Actually, you get a couple % of electrons due to various imperfections. And then when it comes around here, you get the maximum number of electrons. So everything works according to this V minus A theory. Really very beautiful. Now, the last consequence of V minus A that I wanted to talk about, and again, this is some kind of general particle physics that I hope you folks are aware of, but let's take the test. The V minus A theory says that the coupling of the weak interactions to electrons and to muons is universal. In both cases, it's governed by the coupling of U and D quarks to the weak interactions and then to electrons or muons. But there's a famous regularity that you can observe in nature, that the rate for pion decay to electrons over pion decay to muons is 10 to the minus 4. Actually, I should actually have the number on these slides. Yeah. So, one might ask, if the weak interactions are universal with respect to leptons, why is it that pions never decay to electrons? They always, in practice, decay to muons. Who knows the answer to this question? Yes?
Because of the mass, right? I mean,
why? Oh, you're absolutely right.
yeah, the mass mixes the left and right.
So this number is ME over MU squared, times some other factors that are not so important. And this number is 10 to the minus 4.
It's proportional to the breaking of the symmetry, right?
What symmetry?
The chiral symmetry.
Yes. But ultimately, that goes back to V minus A. So let's draw the picture. Here's a pion. It's going to decay to a muon, let's say a mu plus, and the neutrino. The neutrino, if the spins of the neutrino and the muon were arbitrary, if you did not have an absolute selection rule, then these spins can be anything, and this process wouldn't be suppressed by chirality. But in the V minus A theory, there are very specific predictions. In leading order, this guy would be left-handed, this guy would be right-handed, the total angular momentum would be 1, and this would be totally forbidden. A perturbation, which you could imagine, is to have a chirality flip here so that you can get out a mu left. But remember, this consequence is proportional to the square root of E minus P, which is proportional to the muon or electron mass. And so, if you can't do this, which is the maximal thing, but you can only do this, you get a suppression proportional to the mass, which then gives this factor in the relative decay rates. And, well, ordinarily you could do this, but with V minus A, or ordinarily you could just have this go. But it's V minus A that tells you that this is the maximal process, and you need to violate some symmetry to actually get a result consistent with angular momentum. So it's remarkable. V minus A is kind of everywhere. And so this is a property that we're now, if you like, I mean, it might turn out beautiful in the end, but for the moment we're stuck with it. Because now let's come back to the point that I made at the very beginning of the lecture. That a mass term in the Dirac equation is proportional to psi left dagger psi right plus psi right dagger psi left. And so in order to have a mass term, you have to be able to quantum mechanically mix the left-handed and right-handed components of the fermion field. But now what I've shown you is just absolutely true from experiment, is that this guy couples to the weak interactions, and this guy does not couple. And so this term is just, it just has to be 0, unless we can do something clever about it. And so now we're probably in the territory that's very familiar to you. That clever thing involves the Higgs boson and spontaneous symmetry breaking. So now we can back off from experiment a little. I just need to write some formulae that are just extremely familiar to you. So let me do that. Let's turn off this guy. So now we have to make some gauge assignments for the various fermions. So for example, for the electron, we want to put the electrons in some structure like that with the neutrino and the electron. Maybe I should say there are two ways to do this. One way is that, let's start with an SU2 group. One way to do this is to assign the electron to a multiplet like that, which is isospin 1. The other way is to assign the electron to a multiplet like this, which is isospin 1/2. In this way, we can have there's a nice consequence that we can have. That we can write a model which is pure SU2, where the weak interactions will be the isospin raising generators and the isospin lowering generators, and the electric charge can be proportional to I3. Let's say it is I3. Then we can have a symmetry breaking where SU2 is broken to U1. For example, by having a Higgs in the 3, which gets an expectation value like this. This thing can be the photon, and we get two massive W bosons. This is a very attractive model, but please notice it has the property that there is an allowed mass term. The isospin 1 representation is real. We can, if you like, we can assign some way to give mass to the electron. And actually, I think in this model, the Higgs boson is not actually needed to give mass to the electron. You just need some kind of seesaw structure. This is called the Georgi-Glashow model. And it actually was proposed as a serious weak interaction model in the early 1970s. The other way to do it is to modify this formula. That is, to write the gauge group as SU2 cross U1. This requires a new quantum number called hypercharge. Assign this guy hypercharge 1/2. Assign this guy, minus 1/2. You assign this guy also hypercharge -1. The electric charge is assigned to be I3 plus Y. So these two guys have the same electric charge, but they have different fundamental charges, different isospins. This is isospin 0, and different hypercharges. And in that case, to connect them, you really need something also with an extra field with non-trivial quantum numbers. So this is the Glashow-Salam-Weinberg model. henceforth the standard model. And the difference is that because you have another boson here, you are breaking down SU2 cross U1 to U1. This is identified with the photon, but there are 3 massive bosons here. And, well, you folks all know we observe 3 massive bosons in nature. So that's the one that wins according to what nature chooses. Okay, let me quickly write the basic formulae for this model, which I think you've all seen before, and then we'll work from that into the next part of the lecture. Oh, please notice the name Glashow associated with both of these models. Yeah, just because you've written down one good model doesn't mean you shouldn't write down lots more. Nature chooses. Yes?
This E nu E,
Yes?
is it a postulate of a triplet of SU2? And if so, what's E?
Oh, well, that's also part of the problem. E has to be a massive lepton, a massive heavy lepton. So there were 2 things, actually, that gave people, that caused people to reject this model. The first one is that there's no Z boson in it. The second is that searches for the E were made, and people were discouraged by that. Although the E was only searched for up to about 40 GeV. So with our current understanding, we should say, well, you should just wait until the limits on the E get to be hundreds of GeV. But of course, then the neutral currents were discovered, so then there was much less motivation to go there. I mean, now we know that this guy is excluded through its whole range. But in the 1970s, that was not known. But when I first learned about this model, as I say, back in prehistory, the reason given for rejecting it was that this E didn't seem to exist. Okay. Okay. So I guess the next thing to do is to write the couplings of this model. And let me write them in the following way. The SU2 cross U1 means that there are 2 independent coupling constants, which are called G and G prime. There's also the combination called E, which is GG prime over the square root of G squared plus G prime squared, which is identified with the electric charge. It's the coupling of the photon. So the delta L for this model is G over the square root of 2 times, let me just write this for leptons, the nu bar sigma mu E times W plus E bar sigma mu nu times W minus. The E coupling, and this is always the left-handed, the E coupling is any fermion sigma mu or sigma mu bar times I3 plus Y times the photon. So this quantum number is the electric charge, and is the electric charge in units, in natural units, and this is the electric coupling constant, which is given by that formula. There's a weak mixing angle, sine theta W, which is equal to this. And the Z charge is given by G over, I'm going to call this SW and the corresponding cosine CW. G over CW Z mu times F bar and then sigma mu F and then the Z charge. And the Z charge, one should probably commit this to memory, is I3 minus sine squared theta W times the electric charge. So you've all seen this formula derived in your quantum field theory course. Yeah, raise your hand if you've seen this formula derived. Keep your hand up if you've committed this formula to memory. Oh, okay. Well, you can always Google it. Okay. With this formula, we can discuss a number of things, but I think the thing which is most important to us now is to discuss the pattern of charges of the Z. And I have that on a slide. I'd like to show it to you. I think that's the next slide here. Oh, God. Lost control of this. Yeah, here we go. Okay, this is very important. Because the numbers here are also important. Maybe I should turn this off. So here's the formula that I wrote for the 4 species of the standard model for each generation. Nu, E, U, and D. So this is just the literal version of this formula that I wrote here. What are these SF and AF? SF is the Z charge for the left-handed plus Z charge for the right-handed particles. And AF is the polarization asymmetry, in the same way that I've defined it before. And now, this is something that you should appreciate, because it's actually a very cool feature of the standard model. This formula looks totally regular. It's like, it's the same thing, just repeated over and over again for every species. But these numbers here are all over the map. And it's very interesting to ask. So I put in SW squared is equal to 0.231, which is a number which we have to defend from, this is determined from experiment. So we have to defend that from experiment. But for the value that's going to give a good fit to the data that I showed you, that's a reasonable value. And so now you see these numbers are all over the map. So for example, this number is the smallest one. That's the Z rate to leptons, the sum of the squares of the left-handed and right-handed charges. The quarks, of course, get amplified because you multiply those numbers by 3 for color and another 4% for the QCD correction. So it means that the electron and muon and tau decays of the Z are going to be swamped by decays from quarks and also from neutrinos. The neutrinos, there are 3 species of neutrino. So that's also a quite large number, 0.75. And so substantial numbers of Z decays are going to be to neutrinos. Actually, it's a 20% branching ratio. And this is something that figures very importantly in LHC phenomenology. Maybe I should ask, how many of you already knew that Z to nu bar is a very important feature of LHC phenomenology? Sorry? I'm sorry? Well, no, because this is a background to all missing energy. Right, if you want to find supersymmetry at the LHC, you look for jets plus missing energy, but the dominant thing you see is Z to nu bar plus multi-jets produced from the QCD part of that interaction. So the fact that the leptons are, and the way you positively identify Z's at the LHC is through the leptonic decay, Z to E plus E minus or Z to mu plus mu minus. So the fact that the leptons are small and the neutrinos are large is actually a difficulty in LHC phenomenology that probably many of you have run many Monte Carlos trying to overcome. For the purpose of this lecture, what's interesting is that these numbers are all over the map, but they're also directly measurable in a set of experiments that were done in the 1990s. And so let me finish the lecture by discussing those experiments. So if you have a Z coupling to E plus E minus, you also have a E plus E minus coupling to Z. And so if you have a lepton collider, you can actually take that lepton collider, adjust the energy to be, of each beam to be exactly half of the energy mc squared of the Z. So that would be 91 GeV divided by 2. Collide electrons and positrons together. As you adjust the energy, the Z, there's some background level, and the Z should appear as a resonance with a height of about 1,000 times the background. Then, if you're lucky, you can just sit here, and everything you're observing is Z decays. So this is now the energy of the collider. And you can just basically check off these numbers one after another. And so this was done, I guess probably with the most Z's at the LEP-1 collider at CERN. Also with a smaller number of Z's, but with some advantage we'll talk about in a moment, at my lab, SLAC. SLAC accumulated about 500,000 Z's, and CERN, with 4 experiments, about 20 million Z's. And then you can just look at every final state and see to what extent you can verify these numbers. So let me just show you a few pictures of this. And I think if you look into this more carefully, it's really a very interesting program. Here's, by the way, the calculation of the total Z width. It's just tree level that comes from these numbers. So you can see the contributions from nu, E, U, and D. The 3 is the number of generations. The 2 here is 2 generations because, of course, the Z is not massive enough to produce the top quark. This 3.1 is the QCD factor. It all adds up to 2.49 GeV. That's, even though this is a tree level calculation, it's in very good agreement with the experimental result. And here are the branching ratios that you get. And in particular, as I said, 3 times this number is 20%. So there's a very substantial rate of the Z to totally invisible final states. Here is an interesting distribution. This is a very simple selection of the events. This is E charge, the charged energy, and the number of charged particles. But you see it really qualitatively separates all of the various kinds of events. Totally leptonic decays are in the back corner. Taus are in this corner. Let's see. This is some background process. QQ bar is a wide distribution in the center, so I think this maybe is more clear on the next slide. The events just separate into categories. And if you're a person, you could just take a stack of 20 million pictures and just sort them out into categories to measure the branching ratios. Here is the line shape. Actually, I think I'd like to show you this one first. This is the measurement of the line shape by the Opal experiment at LEP. So you basically take steps in energy through the resonance. The black is the theoretical prediction based on the position of the resonance gives you the value of the Z mass. And as you know, as we will discuss maybe in a little more detail in a moment, the Z mass is linked to other parameters of the theory. So the parameters of the theory that are relevant are G, G prime, and V, the Higgs vacuum expectation value. So there are 3 parameters. You can trade these 3 parameters for 3 more observable parameters, namely alpha, G Fermi, the strength of the weak interactions, and the mass of the Z. And probably you should renormalize alpha up to the mass of the Z, because otherwise you incur a large radiative correction. So this is the renormalization group running from 137 up to mz, which makes this value about 129. From that, you can infer all of the parameters of the standard model, and then you can predict the resonance curve. The resonance curve it's quite interesting, and I don't have time in this lecture to discuss all the features of it, but it's something that you might want to look into. The most important aspect of this is that if you have E plus E minus to Z, in that process you can radiate photons from the initial state. And this turns out to be quite a large effect. The effect is alpha times the log squared of S over ME. And then there's another factor that comes in. So this number is about 0.1 at the Z mass. There's another factor that comes in, which is the width over mz. So that says that if the Z is narrow, if there are many photons, the spectrum will be distorted. And this whole quantity turns out to be about 40% for the Z experiments. So in fact, what happens is that the electrons and positrons annihilating at the Z aren't quite at the energy of the Z mass. They have to be at a slightly higher energy in order to take into account the radiation of photons. And I think that that's shown on this slide. So the red curve is the not radiatively corrected cross-section. The green curve is the radiatively corrected cross-section. The points are the average of the 4 LEP experiments. And there's a little note here that the measurement error bars are increased by a factor of 10 so that you can see them. And so it's just a fantastically successful validation of the various SFs that appear in the theory, the total rates. Now, more interesting than the SFs maybe are the AFs. Because although the SFs have a large variation, the AFs are really all over the map. Of course, the neutrinos are not observable, so let's not talk about those. But you see that the leptons have a 15% left-right asymmetry. So from the numbers which are written there, you can see that sine squared theta w is somewhat close to a quarter. So these numbers are both close to a quarter in magnitude. And that means there's a relatively small preference from the Z, as opposed to the W, for left-handed electrons relative to right-handed electrons. If you calculate the asymmetry in this way, it's a 15% asymmetry. On the other hand, for down quarks, there's a third that comes here. A third of sine squared theta w is a 12th. You square it. And so there are hardly any left-handed down quarks, or for that matter, bottom quarks, produced at the Z. They're all left-handed. And so the asymmetries are very small for the leptons, larger for up quarks, and essentially maximal for down quarks. So you ought to be able to just look at the data and see this. And there are various ways to do that, which are quite interesting. Here we go. Let's skip by that. Let's skip by this one too. Let's talk about this first. So in particular, a lepton which is very accessible is the tau lepton. The tau lepton decays by weak interactions. Essentially, it's the same decay mechanism that I showed you when you go to leptons for the muon. The tau can also decay to hadrons. That is to say, the tau couples to the weak current J+, which can then materialize as a pi, a rho, etc. The decay tau to pi nu is especially simple. And maybe it's worth just talking about that a little. The tau, let's say the tau is left-handed. Its angular momentum points this way. It decays to an electron, let's say to a neutrino and a pi meson. The neutrino is always left-handed according to V minus A. The pion has 0 spin. So you can see that this configuration is totally allowed by angular momentum. On the other hand, if we turned it around, if the neutrino decayed backwards, in the backward direction, then it wouldn't be allowed. Angular momentum would be violated. And so for a tau moving in the 3 direction and polarized in the left-handed sense, it goes to a fast neutrino and a slow pion. A tau in the right-handed sense would decay to a fast pion and a slow neutrino. And in fact, it turns out that the decay rates are proportional to the energy of the pion. So this is the prediction. This is the prediction in red for a left-handed tau emitted from the Z, in the green for a right-handed tau emitted from the Z. If the Z decayed equally to left and right-handed taus, the slopes would cancel and this distribution would be flat. The energy distribution measured by the Olive experiment is shown on the slide. And you can see that there's a slight excess of this over this. And so if you actually work it out, it's this 15% asymmetry. And then you can see this in a large number of tau decay modes to hadrons, and actually also in the tau decay mode to muons. So that's one way of verifying this 0.15 that I wrote for you for the leptonic side. Now, there's another way to do it, which we did at SLAC, which is actually extremely cool. If you have a polarized beam, you could directly measure the separate rates of E left and E right producing the Z resonance. And so the way the experiment is done is actually mostly done when you actually create the beam itself. So this is the device that was used to create the polarized beams. You have some laser which produces circularly polarized light. You have a device here called a Pockels cell, which depending on the voltage that you put across it is an adjustable right-handed or left-handed circular polarizer. It hits a very hard to make strained gallium arsenide cathode, and depending on the polarization, it kicks out electrons from a left-handed or a right-handed, or let's just say one polarization or another electrons in that semiconductor. The electrons are then sucked up into the SLC accelerator system. They travel 4 kilometers down to the interaction region, and it turns out that when it's a left-handed polarized beam, you get more Z's than when it's a right-handed polarized beam. And actually at the bottom of the slide, you see the number for the measurement, so the error is now in the 3rd significant figure. Actually, there are many very significant measurements. If you write this in terms of the value of the effective sine squared theta w, you get some agreement that looks like this. So the top one is from the leptonic forward-backward asymmetry. The next one is from the tau polarization. The next one is from this measurement I just showed you. There are some other measurements which involve quarks. Actually, this one is from the B forward-backward asymmetry. And it looks like it's highly deviant, but you have to look at how many zeros there are in the error. These are the errors people quote. And when you average them all up, it turns out that you get a value of this sine squared theta w, which, as I said, 0.231 with the error in the 4th decimal place. So at the same time, you can, with this polarized beam, you could try and measure the bottom A sub B, the one that has to do with the down quarks, by looking for bottom quarks. Now, at the very beginning of the lecture, I told you that if you have a left-handed electron beam, and you make left-handed bottom quarks, this is a 1 plus cosine theta squared distribution, very peaked forward. If you have right-handed bottom quarks, this is a 1 minus cosine theta squared distribution. So if the Z hardly ever decays to bottom quarks, you get a 1 plus cosine theta squared distribution when you have a left-handed beam. But then with a right-handed beam, everything flips, and you get the 1 minus cosine theta squared distribution. So it should then be totally obvious. You start with a left-handed beam, you make Z's, the B's all go forward. Start with a right-handed beam, make Z's, the B's all go backward. Now it's not totally obvious how to tell a B from a B bar in this situation. So you can't do it perfectly, but you can see that the data is qualitatively in agreement with this prescription. When you have a left-handed beam, it's highly forward peaked. When you have a right-handed beam, it's highly backward peaked. And actually, the difference in the normalization is that 15% leptonic uncertainty that we just talked about. So, well, it really works. There's a lot more to this stuff. I recommend that you study it. This is probably something you have seen before, the final table of agreement with a long list of precision electroweak observables together with the best fit value of the 3 standard model parameters that I had written up here. And as you see, the structure now works extremely well. This is the number of sigmas deviation. But take that together with the ones that have the biggest deviations also have the smallest errors. So this is a theory, this SU2 cross U1 theory is a theory that's working extremely well to describe the structure of the weak interactions. Okay, it's 10:30, I'd better stop. There's one more chapter that I had in this lecture, which is S&T, and I think I'll postpone that to tomorrow. So thank you very much.